and also sometimes with geometric flavor. So today he's going to talk about the Landau-Lifshitz-Gilbert equation, and he gives 4 lectures this week. So, is it slow?
Yeah,
Let us welcome.
Thank you, Sri, for the kind introduction. Thank you all the organizers for organizing this great meeting. And as you said, this week I will speak about Landau-Lifshitz equations. I usually speak very loud, so do I need it?
Yeah, it's recording. So.
It's recording. And how should I switch it on?
There's a switch.
On. It should be in the middle, or it's on now. And so it just repeats. Thanks to Sri for the introduction to organizing this beautiful meeting. And today I will only begin the series of my 4 lectures, and I will speak about Stratonovich integral. The reason for this introductory lecture is that the equation I will speak about are written down in Stratonovich form, and not just so because somebody likes it, because they have to be, for intrinsic reasons, to be written in the Stratonovich form. And sometimes people don't understand what it is really. So I wanted to explain what does it mean, a Stratonovich integral, a stochastic differential equation in Stratonovich form. So I will begin with something which has not been done understand before, which is the Ito formula. So I just write it down because we will use it. So what are our assumptions for the whole lecture? We have a filtered probability space. We have a Hilbert space X, and you can always imagine that the Hilbert space X is just Euclidean space RD, and we have 2 processes. Okay, still good. So we can consider 2 processes M, which is in the class M1 0 capital T X. So we fix T positive to simplify, and what this means is that A is progressively measurable with respect to our filtration F, and the expected value of the integral A of T to the power 1 is finite, and B belongs to M2 0 dx, which means that B is progressively measurable, and expected value of B of T squared dt is finite as well. And with these 2 objects, we can consider a process psi of t, which is psi 0 plus the integral from 0 to t psi of s, a of s, plus integral from 0 to t d of s, dw of s. So I didn't say what is w. So, but that was said before. So in this case, we assume that w, I write it this way, is r-valued f in a process. Now, a comment is that for simplicity, really, write everything about one-dimensional Brownian motion of linear processes in the notes, which I'm moving forward in finishing preparation. Everything is done actually much more general. for Banach space valued processes and Wiener processes as well. So then the formulations are much more complicated. But in order to understand, one needs to understand this simple case. So then, because I want to speak now about Ito formula, so we take a function f, which for simplicity, we just assume to be time independent. Also in my notes they are still, but so we take a function f from x to x, which is a C2 class. So when its space is finite dimensional, if it's C2 class, the second derivative is bounded on balls, because balls are compact, but in general, we just assume that the second derivative is bounded on balls. Actually, then I'm not very precise, but the point is that we need some assumptions to, but let me write it down, although it is not the formula here. So we need a little bit more assumptions. And then what we say, we consider the process f of psi of t, and this process have this representation as in semi-martingale, because psi is a semi-martingale or Ito process written by that formula. This is just equal integral plus integral from 0 to t f prime of psi of s a of s ds plus the Ito integral plus 1/2 second derivative of psi of s b of s ds. That's my Ito formula. So actually, one needs some gross assumptions on the function f, unless one wants to introduce same stopping time, etc. So this C2 class plus some gross conditions, but these are technical and can be easily understood. Just the formula is that to understand what it is that, so f is a map from x to x. So by f prime, I mean the Fresher derivative. So f prime of psi is just Fresher derivative of f. Which means that there's a linear map from x to x linear. And therefore, if I apply this object to a vector A in the space X, this is an element of X. So we've got X-valued process. The same we have with f prime, and the second order derivative at the point psi is bilinear map from x to actually this f could be take values in another space, say y. So we can have not just x but two Hilbert spaces, and if I the process psi takes values in x, but the process f of psi can take values in different Hilbert space, and doesn't really matter. So this way we only have to correct here. We have y. So that's, roughly speaking, it makes sense. And I say if we put some growth conditions on f, so the growth condition would be that, for instance, but they can weaken that if A belongs to this class, we want that this process belongs to this class as well. So put it this way, that will be the Ito formula I will need today. And the topic of my presentation today is the Stratonovich integral, which is closely related to Ito formula. And by examples, I will explain why we need this Stratonovich formula. So what we consider, say, definition. And so what we consider is the process psi of this form. So let psi be of form 1. And then we assume that g is a function from x to x of C1 class. And we want to define what does it mean, the integral from 0 to t, g of psi of r, dw of r. And the definition at this moment will be completely formal, and you see no reason to have this definition. So I will try to explain it by examples and by some properties. So we put it to be equal expression of the integral of the following form. So here this circle means Stratonovich. So what we have, we consider integral from g of psi of r, the normal Ito integral, plus correction 1/2 0 to t g prime of psi of r b of r dr. So I explained before the meaning of g prime, so it is the same as here. So the g, because b is a random variable taking values in x, g prime on this guy is again something which takes values in x. And this is for every t larger or equal to 0. Oh. So that is our Stratonovich integral. Now, why do we need it? What you notice is actually that this 1/2 is the same as in the Ito formula. However, in the Ito formula, we have second order derivative. Here we've got only first order derivative. And now we consider the second part of the definition. Because here we define Stratonovich integral, we want to define a Stratonovich differential equation. So we can say a process psi, and we always take t from 0 to capital T to fixed, is a solution to equation. So this we can call 2, this we can call 3, and this equation is d psi equals f of psi dt plus g of psi Stratonovich dw with initial condition psi of 0 equals psi 0, if and only if psi is a solution to the Ito equation of the similar form. So this equation 5 is d psi is equal f of psi dt plus g of psi Ito dw plus correction 1/2 there is no, we don't write the integral, so it's 1/2 g prime of psi t g of psi of so I don't write t, so I don't should g of psi dt. And whenever we have written something, we need to check at least that the formula which is written down makes sense. And here, if you want to consider this equation, what we need to say about f and g. So f is a vector field on x.
So here the Stratonovich here, B is psi, right?
Here is b.
And there you are using G.
Sorry?
So B is given for you.
So there are two different concepts. Yeah, so which are related. So one concept is that if you have a Ito process of the form 1, you define a Stratonovich integral for every function g applying to psi. So maybe instead of g, because the g over there is used for different purposes, we can just use a function phi. Yes? So in particular, so you can have phi. And but here we just have an equation. So in this equation 4, f and g are vector fields on the space X. So because they are vector field, and we assume that this is, for instance, Lifshitz, and this is, we can see that is C1 where G and G prime bounded. Maybe also we can say Lifshitz and bounded. Because, so this expression again makes sense because G of psi, element of X, G prime is a linear map, so this is an element of X. Yes? So it is just very formally. I didn't say why it comes from. So we define a solution to Stratonovich equation when it is a solution to the Ito equation with the correction term. We defined Stratonovich integral for any function phi, for any function phi, as the Ito integral plus a correction. Now, what I want is the following result is the main sort of theorem. The property is the following, that put it the theorem. So suppose we have a process psi which solves our equation 4, which means solve equation 5. Yeah, so suppose psi solves equation 4. And suppose also that phi is a map from X to another Hilbert space Y, and this phi is of C2B class, which means C2 class, everything is bounded, just to avoid any problems. And then we define a process eta by formula eta of t equals phi of psi of t. And then what we claim is that then this process eta solves this process eta satisfies the following identity where the integral is in the sense of Stratonovich. So the identity is the following. Let me write it down. Eta of t is equal phi of psi 0 plus integral from 0 to t phi prime of psi f of psi plus integral from 0 to t phi prime of psi. Sorry, so here's everywhere should be s. Psi s g of psi s Stratonovich dws. So because of shortage of space, I just use s instead of bracket of s. So what we claim is that this identity here, 6, there is a Stratonovich integral, and this Stratonovich integral is meant as a Stratonovich integral in the sense I have defined before. So let me explain this because, and there's another thing here, is that if you so this is something like an Ito theorem. Yes, but the Ito theorem, because you have a process psi, which is maybe not, but we start with this process, and then we apply the formula phi, and then we would have Ito formula from the bottom of that blackboard. But if you compare the formula 2 to formula 6, there is no second order derivative here. There is a second order derivative over there. And actually, I assume phi to be of C2 class, but there is no phi second order derivative here. So I can actually suspect that you don't need phi to be second class to get this theorem. And actually, this theorem is a version of Ito formula. It follows from Ito formula. So what it only says is that if you define some object, which is this Stratonovich integral, then the Stratonovich integral behaves more like classical. So for Stratonovich integral, we have more like classical differentiation rule instead of the Ito rule, because there is no second order derivative, no correction. Yeah, so we started with the process, this one. We applied psi, so we got phi prime of psi acting on F. Then we've got G of psi integral, and here we've got phi prime of psi acting on G and Stratonovich integral. The same rule as in the classical analysis. So let me try to explain this. And one is that I will have to work with little space. So I try to use this blackboard